Hello everyone, my name is Boyun. My co-authors are Peng Zhang and He Zhang. We are with the University of Louisiana at Lafayette. The paper I'm presenting is mathematical modeling of a heat transfer from geothermal reservoirs to gas hydrate reservoirs. Basically, it's a thermal stimulation of gas hydrate reservoirs. I'm going to make a brief introduction to gas hydrates, followed by heat transfer system we proposed, then mathematical modeling of heat transfer processes. Then we move on to case study, and finally conclusions. Gas hydrate is a compound of water and gas. Small molecule gases are trapped in water to form solid. These small molecules are methane, ethane, propane, isobutane, CO2, H2S, etc. They form hydrate or solid phase of water under pressure, under high pressure and low temperature conditions. For methane hydrate, about 160 times the volume of gas is trapped in the hydrate. There are three types of structures of gas hydrate classically. Type 1, type 2, type H. I don't have time to define these structures. Hydrocarbon hydrates are also called combustible ice or burning ice. We can find gas hydrates in permafrost and ocean floor. In permafrost, gas hydrates are buried in the depths between 200 meters and 1200 meters, where you have a temperature below the hydrate and gas phase boundary. You have a stable gas hydrates. In ocean floor, gas hydrates are buried between the ocean floor and 1500 meters, where you have a small envelope allowing the gas hydrate to stay in stable condition. A lot of gas hydrates have been found in the world. The total reserves range from 10 to power 15 to 10 to power 19 standard cubic meters. People say if 10% of the hydrates are developed to produce natural gas efficiently, the energy can support the world for 180 years. Currently, the challenges in gas production from natural gas hydrates include low well productivity, sand production, and variable collapse. All of them are related to production method called depressurization. If we use heat to dissociate natural gas hydrate, it's not economical. It's cost too much money. So in this study, we're going to use geothermal heat to stimulate gas hydrate reservoir. We propose to use well structure called a Y-shaped well structure to transfer heat from geothermal zone to gas hydrate zone below the mud line and offshore. The heat transfer system involves water injection from the surface to geothermal zone, where the water is heated and returned to the wearable in the gas hydrate zone, where the water dissipated heat into the reservoir, heating the gas hydrate to cause dissociation of gas hydrates. The free gas is produced by these horizontal variable we call the gas producer. This is a low-cost operation because we do not provide heat energy. We provide only small amount of energy to drive a water pump. Mathematical models. We have developed two sort of models. One is called the Inter-Wearable heat transfer model, where we divide the variable into four sections. The first section we have unit one direction flow to provide water flow. Then you have a counter flow in the vertical section. They have counter current flow in the horizontal section. You have one direction flow in the variable in the gas hybrid zone. I do not have time to describe these analytical models, but I will show you the result. The second kind of model is called the variable to reservoir heat transfer model. We solve the governing equation for heat conduction. We got the time and the space dependent temperature distribution in the gas hybrid reservoir zone. Of course, the heat transfer depends on temperature drop of fluid in the horizontal variable, depend on mass flow rate, and also heat capacity of fluid. To validate the analytical model, we solve the equation numerically. Here we plot temperature profile obtained from both analytical solution and numerical solution for different types of water injection. It shows they are very consistent. Then we move on to a case study. We obtain data from an area called the Shenghu area in the northern and South China Sea, where we know water depths, we know geothermal gradient, we know the geothermal the zone, we know gas hybrid reservoir depths. We use the model to investigate the effects of several parameters. One of them is the water flow rate. The effect of water flow rate on heat transfer is plotted in this graph. It shows the temperature versus the depths. Basically, we're talking about the temperature in the annulus and in the pipe in the section 2 and section 3 sections. The temperature in section 3 is the highest. We have a geothermal temperature. When fluid flows up to the top of section 2, the temperature drops to this value, depending on flow rate. If the flow rate increases from 0.004 cubic meter per second up to 0.01 cubic meter per second, the temperature increases from 29 degrees to 40 degrees. That's the temperature of water delivered to the horizontal variable inlet. Secondly, we analyze the effect of well depths on heat transfer. The well depth is defined as depths from surface to the bottom of vertical section. As we drill deeper and deeper, we expect to have hotter and hotter water from the horizontal variable. But in reality, in fact, model shows that we have heat loss in the vertical section, causing almost the same deliverable temperature to the horizontal variable. See, the depth changed from 750 to 1,500 meters. The temperature in the pit zone, in the lower section, increases about the temperature at outlet of the section 2 or the inlet of the section 4, almost the same. Third, we investigate the effect of vertical hole cement thermal conductivity on heat transfer. we talk about the cement thermal conductivity in here. We want to have a low conductivity so that we do not lose a lot of heat. When we reduce the thermal conductivity of the cement from 0.54 down to 0.1, the delivered temperature increases from 18 to 40 degrees to that point because of better insulation. First, we analyze the effect of a horizontal hole cement thermal conductivity on heat transfer. We are looking at thermal conductivity of cement in this horizontal wearable. With the same value of temperature, which is 40 degrees at the inlet point, the temperature at outlet drops when the thermal conductivity increases from 0.1 to 0.54. So that drop reflects the temperature change through this horizontal wearable, meaning that more heat dissipated into reservoir to dissociate the natural gas hydrate. We also look at the wearable to reservoir heat transfer model. The result shows temperature profile as function of radial distance for different times of water injection. And water injection time goes how long the temperature rises near wearable quickly. This graph shows the temperature plot for the time for a different location. Again, near wearable, the temperature increases quickly. Finally, we look at the temperature profile, the temperature front of 15 degrees Celsius, which is hydrate dissolution temperature. The result shows the radial distance of front from wearable increases slowly with time. Over 2 years of time, the temperature per front, the 15 degree temperature front goes up to 20 meters from wearable. Now I move on to a conclusion section. We have 4 conclusions. First, the analytical model for heat transfer inside reservoir was validated by a comparison with value result and the result given by a numerical model for arbitrary data set. Second, applying the analytical model to the gas hydrate reservoir in the Xinghu area, North and South China Sea, allowed for prediction of temperature profiles, both in spatial and time domains. Model result reveals that the natural gas hydrate reservoir temperature should rise quickly at any heated affected point, but it should propagate slowly in the radial direction due to the low thermal conductivity of a reservoir. Third, it should take more than 2 years to dissociate gas hydrate within 20 meters of a heat dissipator wearable due to only thermal stimulation. Therefore, the geothermal stimulation method should be used as a technique for accelerating gas production with a depressurization scheme to reduce pressure reduction. Fourth, the analytical model shows that the heat transfer is controlled by fluid mass flow rate, weakly influenced by well depth, and strongly affected by thermal conductivity of wearable cement. This project was supported by Bird. Thank you for your attention. If you have any questions, I'll be glad to answer them.